Hello, guys. Welcome to day 2 of task analysis session of CyBRICS 2021 CTF. So, yesterday we have the web day and the MISC day. Today we will have phone day and network day. Unfortunately, today I'm not joined by anyone. The phone task author Егor maybe will join us later and tell us about his task in person, but he is kind of busy right now, and he prepared some recordings just in case if he doesn't make it in time. So let's begin with the challenges that got the most votes. And I will start with the network. First challenge that I'll cover today is Network Easy LX100. So we're given a pickup traffic dump. Let's look into that. And that should be some dump of, here I have the dump, I loaded it. And let's see what we have here. Here we have some control commands over HTTP to the camera, it seems like. And starting not too far from the beginning, we have a lot of UDP traffic, and it continues towards the end. This is the fragmented UDP packets. Well, the fragmentation is needed because the length of the UDP packets is 25 kilobytes, and the maximum segment size is like 1.5 kilobyte. Wireshark helpfully just stitches together the UDP and allows us to see the entire data, which is 25K. So let's try to analyze what those UDP packets are. For example, let's maybe save one packet and try to look at it. Let's copy it as copy the data as raw hex stream. This way we can open up a hex editor. For example, I'll create an empty file and open it in hex editor and paste it as hex. And so here we have our file. And for the keen eye, we can spot right away that not far from the beginning of the packet, we have FFD8, FFDB, which is a signature of JPEG data. So it looks like our camera just sends out just plain JPEG frames or pictures over Wi-Fi encapsulated in UDP. So, all right, let's try to see what's inside those JPEGs. For example, let's just remove everything that's before the JPEG signature. Let's check the ending. And the ending is FFD9, which is the correct ending of the JPEG. So, let's rename it to the JPEG and see. Okay, we got ourselves some picture. Nice. Now, I think we'll need to extract all the frames, right? And the way that I propose it to be solved is like this. Let me open up a bigger console. Yeah, that's good. So I propose first extracting all the UDP packet data with T-Shark. Like this, we read from the file. We filter by UDP, I guess. Maybe even UDP destination port. Can I copy that filter? Yes. UDP destination port. And we extract field, which is called data, maybe. Right? Yeah. So T-Shark gives us one hex dump of the data per line. Let's redirect it to some text file. Okay, here we have our packets, and now we just have to unhex them. Let's quickly do that. So frame i.jpg, and we just unhex the value on the line. How many parentheses do I need? Seems good. Okay. We have extracted 455 frames. And let's check them using an image editor, image viewer. Okay. Looks like it's a live stream of pictures. I'm currently scrolling between the frames. And okay, here is the flag attached to the window. Lost secrets in the air. Okay, this was my solution. And like yesterday, you can ask your questions in the YouTube chat. Please do if you have any questions or comments. I'll check it from time to time and try to answer them. The next challenge will be, again, network, now medium. Network medium, future tech. So, we're given a strange looking link. They say your flag is at HTTP3 over DCCP over IPv6, this domain. Okay, looks like it's an implementation challenge or something to use some strange futuristic protocols. Let's fight it one step at a time. Let's peel the layers one at a time. So first of all, IPv6. I personally do not have IPv6 at my home network, so I'll just need some cloud VPS, for example. I have one now, just not to create it at the spot. Actually, again, let me use a bigger console. All right. So, do I have IPv6? Yes. Let's ping the domain. Do we have connectivity? Yeah. The host responds over IPv6. Now, let's build the DCCP part. Since DCCP is not widely used protocol, and normally HTTP3 works over UDP, I choose to just make an adapter that receives packets over UDP and sends them to the host over DCCP. For making adapters, SOCAT is really good. So let's Google like SOCAT DCCP. Does it do DCCP? And right at the official website of SOCAT, we see that we can use actually overriding of a socket type and protocol with a TCP SOCAT option to actually convert the TCP socket to DCCP. Let's do something like, well, let's first install SOCAT. Oh. And let's do something like, what would it be? SOCAT UDP listen on port HTTP3 is 403, normally fork, raise other, and then connect over DCCP, like this. TCP6 connect, because we have IPv6 to this domain. Port, well, there is no port, but the default port for HTTP3 is 443. And, well, I guess it looks okay. Let's try like that. And also, maybe we'll enable debugs. Okay, so we got socket listening. What can we do to check? Let's just send some UDP packets to it to check it separately. New tab. I don't know. Let's just say hello. Okay, socket has successfully connected to the remote DCCP server. And, okay, looks like the DCCP server decided not to talk to our hello, so we got a disconnect. Okay. Now, we seemingly got DCCP working. Looks like that, but we have one more stage to cover. It's HTTP3. So, let's Google for HTTP3 client. We see that Cloudflare has a reference implementation called Quiche of the HTTP3 client. It's in Rust, and we actually can maybe compile the Rust binary from it. I actually haven't tried that because I wanted to request HTTP3 with curl, since curl is the ubiquitous HTTP tool, so maybe it just has HTTP3 support. And actually it does, but it's experimental. It's turned on with --HTTP3. Let's try --HTTP3. Curl --HTTP3 HTTPS at this IP address. And we have listening on 443. Let's enable verbose mode. But yeah, any curl version that I have tried from the default repos does not have HTTP3 support, unfortunately. So the next thing I tried was to, I tried actually building curl with HTTP3 support, but that involved building the Quiche library, and I just thought maybe someone has already done it and just packaged it into a nice Docker file. And yeah, indeed, we have some results for HTTP3 curl in Docker. And let's just try the first one. Let's fire up our Docker. All right, downloading the image. 135 megabytes. Maybe those are some remaining files after compiling the Quiche and curl. Maybe they have not cleaned the Docker image before submitting it to the Docker Hub. Alrighty. So what do we have here? Curl. Does it support HTTP3? Let's check with the same command. Boom. Wow, we have actually got a response with HTTP version 3. So, hello from future, UTF 8192. And we have a link to an image. Let's download the image. Oh, okay, it's a binary image, of course, so we need to download it. But let me actually mount some directory. For example, MNT to MNT, and change the directory to our current directory. and let's save the image. Alrighty, we're downloading it. And somehow the download stalls. It successfully downloads around 40 kilobytes of data per try, but we can use the range headers, which curl uses automatically if we give it -c. I do not remember if it should be the uppercase C or lowercase c, like continue, and it also needs a dash. Yeah, it requested the further range, again 40 kilobytes, but we can just restart the process. Maybe the network connectivity between present and future is kind of bad. So let's download the entire file. We apparently need 3 more tries. 3 more restarts. All right, and hopefully the last one. Yay! We have downloaded the net100.hike. All right. We have the hike image. I do not have anything to open the hike image, so let's just decode this. Let's decode the hike. I think I had some hike utils in my repositories, but that's not. Maybe that's not the case. Maybe we can use console utilities, or maybe we can just use some first result from Google that allows us to convert the hike to the JPEG. And here is the result. Here is our flag. All right. And yeah, of course, the console tool is called like hike convert net100.hike output net100.jpg. Yeah, the same results. And of course, newer operating systems just get hike decoder built in. So that was Net Medium Future Tech. We do not have any questions in the YouTube chat, so let's proceed with the next challenge. And the next challenge will be Forensics Medium Antarctic by Artur Hanov. And he, again, like yesterday, is only present virtually by recording. I'm going to roll it now. Enjoy. This forensic is, kinda network also, so we decided to move it to this day.
Hello, I will tell you about task Antarctica. Task Antarctica consists of image. It was image of my Windows 10 virtual machine, and in this machine I created some interesting challenge for you. Of course, it may be solved very easy, and it's not difficult for anybody, for any city hacker, but it was modified to more difficult task by next way. This image was published in remote server with speed restriction, so that you cannot just download it. If you try to download it, you will have to spend about 68 days. Here is too many days for full download, yes. So you cannot just download this image, so you have to manipulate with this image remotely with some remote algorithm. It's not too hard to do this, but you need to prepare some environment. It was difficult for me also to find how to do this. I tried to find something like fuse in Python, fuse in C, and create some wrapper for this. But a good solution was proposed for me by Vlad. Actually, Vlad just proposed the full solution of this task, so I will tell you this. I'm saying about this file system, and as it was noted for me, one team tried to use something like this. It's HTTP DFS. It means that you may access some files in your file system with some wrapper which requests all data in remote HTTP server with a range header in HTTP. So if you are able to mount remote reference to your local directory with this tool, you are able to use your common analysis tools like Sleuthkit, like Autopsy, like any other tools to find flag and remote disk. But for these tools, it was some errors, and Vlad also fixed these errors. You can find here that Vlad fixed next things here. First, off by one error in original sources of cache. I also tried to use this tool without cache, but it was errors because it was too slow when to analyze this. Next error was here. When we request blocks which less than block in cache, it returns invalid data. So let's fix this also. Next, here, Vlad also find some bypass in Nginx. In Nginx, we restricted speed of download with 5 kilobytes. That's why you are not able to download full disk. So here, if you download data with 8 kilobyte block or less, then speed restriction will not work, and you are able to download it with 50 kilobytes. It's too very slow, but it's much better for us, yes. Also, that fixed this error. It was error when you are not able to request small blocks, so he fixed this also. And now, to solve this task, we need to mount this remote reference to some folder. Let's look at mount script. First important place here is this DL size. It means size of remote segment to download is 8 kilobytes. So if we look at Wireshark, when it tries to request remote data, it will request it with 8 kilobyte segments. And here use cache, here use several connections, and here it's remote reference, and here it's folder where we want to mount this. Let me create new folder for this. And now I will fix the script to mount it to the new folder. Good. Next, let me run this. Good. It's mounted, and here it will be log of all downloaded data. Good. Now let's look at our folder. It's MMT5, and here we have image EMG. So we need to analyze this. Let me, for example, try to look what does this image do. What is this image? I will take now first setup of this image, and here we see that it is a boot sector because we see 55AA at the end of sector, and it may be noted that invalid partition table, error loading operating system. That's why we can conclude it's operating system hard drive. So let's try to list partitions in this disk. MMLS is a tool which lies in SleuthKit package. We may also try to use, for example, fdisk-l. And here we see that we have two NTFS partitions. We can suppose that it may be a Windows operating system, so we may try to analyze this. So let's try to mount this NTFS disk to our local file system. How can we do that? To mount this, we just need to create a block device from this file with a fixed offset, and after that mount it as NTFS volume. To mount it like a block device, we need to use this command. It's LO setup. After run, it will show us path to block device, and we need to change offset in this file to this offset, because disk starts from this offset. LO setup takes it in not in sectors but in bytes. That's why we multiplies it to 512. Mount. Oh wait, MMT5. Good. We created block device here, and now we need to mount it like NTFS volume. Here it's mount in read-only mode, and also we need this option. I will explain you further about this. I want to evade from remounting now. Steams will be required here, and here we must place path to our block device. Our block device is loop 30, yes, and also I need path to folder to mount. So I will now first create folder, disk 30, yes. And now mount disk 30, loop 30, mount. It will be mounting for a little time. Good. Oh, wait. one more time. Invalid pass, yes. Yes, now I mounted this. Let me ls. Here we see just root volume of our Windows operating system. So also in task description you may find that we need to find virus infection here. Maybe you know, maybe that viruses commonly starts to write itself to registry and write itself to disk. So it's not a good way to find something to disk. Yes, so we need to find virus in registry. If the common key where virus tries to write itself is run branch. I'm saying about C current user software Microsoft Windows current version and run. Viruses try to write itself to this, and after your computer will be run, it will after start from here. So I need to look at current user branch. Maybe also we know that current user is located in anti-user.dat at users folder. So let's look at x30 users test, and here we can find anti-user.dat, and we will copy it to our local bus. After several minutes, or after just 1 minute, we will find this, and we need to parse this file to get run branch. To make it, we need to enter this command. What does it do? It takes this file and extracts current user branch and extracts run content to outrec. So now we see in outrec that after run we have some strange record. Windows exe. Windows exe is not Windows exe is not Windows. Yes, it looks like Windows because Windows doesn't run itself in exe file. Yes, it's not a common file in System32. So we need to copy this file. Let's copy this. This file is very small. It's about 140 bytes, and this is our next step for reverse. Yes, if we open this file in IDA, we can find this main. In this main, we can find this. At first, it tries to open a virus alternative stream in NTFS. here it concatenates the name of program with this name and try to open and read this thread. Alternative stream, yes. And next it gets computer name and it concatenates this and tries to decrypt some virus. If you look at this function, for example, you may find that it XORs something, yes. And if you look at, for example, this function, you can conclude that it is RC4 cipher because it tries to swap something in 256 array. If at first 6 bytes we can find QWERTY, we print our flag in message box and in printf. And it's true. If we look at sources here, it just concatenates computer name and alternative stream content, and after that tries to decrypt itself with some buffer. At this buffer we have flag, yes. So now we need to extract alternative stream, and also we need to get computer name. That's why when we mounted this volume, we need to mount it with streams. So that's why we need this option. Let's extract streams. Get x6b column and virus exe virus. Here we see alternative stream content. It's this line. Okay, this line is needed to decrypt this. Yes, .is/n. Next, we need computer name. If we go to internet trying to find where computer name is stored, we can find that it is stored in system local machine system branch of registry. So we need to copy this file where these settings are stored. Let me try to do this. Disk 30 system copy. This file is too big, so it will take too much time here, and after that we need to extract the content of this branch also with reget program and use it to decrypt flag. Now we copy this and let's extract computer name. Computer name was this, and we need to use this to decrypt flag. So using this K and RC4 algorithm, we need to decrypt flag. I already wrote your solution. You can find this buffer in binary here and here. This is the same buffer. And here I hard-coded now our K. It's content of alternative string and content of computer name. And after that, it just decrypts flag and prints flag and screen and prints it to screen. Let's try to run this. Here it was our flag. CyBRICS did forensic. If we open Windows, you can find here K in registry, and also when we reboot system, we will find that program will be run. Let's start.
All right. Thank you, virtual Artur. And I'm handing it over to virtual Егор to cover the challenge reverse medium Walker. Let's go.
Hi, this is write-up for Walker task from CyBRICS 2021. We were given a walker.l binary, so if we try to run it, just print no and exit. So let's go to the editor and check what this binary is actually doing. Here we're creating some if stream, set called basic ISException function, then we open flag.txt function, and then we try to read some input string and pass this string to the start check function, which is taking a pointer to our input data. And if we see for the line number 15 here, we could understand that second argument is actually a position. If a position equals dot or x22, this function will return 1. If position is higher than x22, we will throw some t1 exception, and otherwise we try to compare with the corresponding symbol of this fake flag string and call again start check function. So let's try to create flag.txt file with such string and Walker, and it's right well done for us. But unfortunately, check system doesn't accept this string, so let's look at some strings from the binary, and we could see that there's another well done string, which also notice that we should add CyBRICS and around our input. let's try to look where the string is creating is which function is using string, but unfortunately rebyIDA doesn't decompile this function well, but we could try to go, for example, in another disassembler, and again there's no any uses of our well done function, but we again see here some strange exceptions. So let's try to starting from beginning and trying to find out is something important here related with exceptions maybe. And if we look to the graph mode in IDA, we could see that there is some separate subgraphs, which is heavily used, for example, CXA and catch function. I believe there is also a start catch function, begin catch function here. Actually, at least latest IDA 7.6 shows actually not only these subgraphs, but also it's able to show which exact exception is catched by this code location. But again, I have only rebyIDA in this machine. So we have 2, even 3 starting nodes. So if we look, for example, here, we could see that we are calling begin catch function, then start check function with 0 as argument and -1, which is obviously will be higher than OX22, so the T1 exception will be thrown. And another place where is some interesting stuff is happening is here. We write no string to this out and called start function. So the main question here, how we could trigger some exception from this code. And actually answer is lies in this code, which is obviously if we go, for example, is binary image, we could see that this is stdi's exception function. And if we, for example, try to Google this function, we could see that there is a 3 flags could be set here: good bit, off bit, and fail bit. Oh, and also bad bit. Obviously, bad bit doesn't not important to us because I already ran my binary when the file wasn't existed. So let's try to create an empty file and run again my working.l file, and it's right no again. And as you can see here, it's the right no, but then it waits for something from me. So, like, for example, I can enter some string and the binary finished its execution. So let's go to the start function and see what's happening here. As we can see, there's again some exception handler. Go to the read function. If we look at this function, we could see that we read some string And then we are created T2 exception and pass this string as the argument to this exception. Obviously, there is some error here because this return is actually not a valid code. Let's return to the start function again, and we can see that here we are taking our input. Then we calculate the length of our entered string, and then we start call makeMove function in a loop. MakeMove function is taking first argument is our input, second argument is a current index, and then we got two variables, global variables named xpos and ypos, which is equals to 0 by default. So let's go to the makeMove function. Again, we either cannot parse this switch correctly, but again, I just go to the binary ninja and look at this function here. Here I already make comments with the corresponding cases, so we create the T3 exception if we are entered L, D, U or R letter. We create T7 exception if we are entered C later, and we are creating T9 exception if we are entered F later. Again, go here. So we could again try to analyze these isolated subgraphs. Here we could see this is our well-done string, which we already saw. But in order to reach this well-done string, the variable checkpoints should be equal to 4. And this variable is written here. As you can see, it's incremented by 1. Also, we could see a call to method of T8 exception, so we know now that T8 exception, we didn't solve it yet. So let's try to check if we are not going to well done. We are going to here. Here we see that we are working with T3 exception, and if we are not reached this basic block, we will go to this basic block, which is working with T7 exception. And again, this basic block must be related to T9 exception because of all other basic blocks obviously not working with T9 exception. We got some basic blocks with T3 exception. This basic block works with T7 exception, and this basic block works with T8 exception. Let's look to the T3 exception handling. We are taking the what, which we are calling what method, which actually will return for us, I guess, this symbol. So this is our char, and if we so what method of T3 exception will return pointer to our char, and then this char list will pass to the process move function, which is, I guess, even can be disassembled, decompiled. So we are creating T6 exception with our parameters. And then we will see that we have some map variable, which is obviously has some rows with length of the 10 elements. And then if okay, let's look to the T6 exception. I did here because it's a bit more quickly to do here. So what we have passed to the T6 exception. This is a X pos and this is a Y pos. So this is X pos, Y pos, and this is field. I didn't know what this field is responsible to, but if we stop some time, we could see that this actually is OK field. And again, there is some checks. These checks are for the X position, these checks for Y position, and this check is actually, we are checking something in the map array here. And this check is actually checking high bit in map byte. So if high bit is set, then we couldn't go to this location. As you can see here, actually I'm going to resume is this row. I believe I didn't know that this function is no return, and we could try to fix it. Okay, now this function looks like a bit more right. And now we are, I guess we'll lose this code. Let's return it, and again, now we could see what's happened here. So if is okay, return 0 for us, we are creating T5 exception. Else we believe we could see this code somewhere here. Okay. If we carefully analyze this code, we could see that we are just setting the previous location as non-available for us again, because we are set high bit of byte our previous location, and then we throw T4 exception. So let's return to the calling function and try to find out where the T5 or T4 exception are handling. Well, this is not obvious actually, but from what we saw already, I could make some assumptions that T5 exception will go to the exit at the end, and T4 exception will just gracefully return from make move function. So we are moved to the next processing of next symbol. So let's try to see now what we are doing with T7 exception. T7 exception is the exception which is thrown when we solve the C symbol. And we'll take the position and the data, and again position is the next position after C character, and data is actually our string pointer. And then we go to the check substring function, which is again it takes symbol from the map and then check the least significant bit, and if this bit is 0, we are again throw T5 exception. As we know already, this is an exit. This is exception leading binary execution to exit function. Then we are, if this least significant bit is set to 1, we are taking some string from the string array with index of moves, where the moves is, as we could see here, actually number of our move. Each character in our input string, control character, is incrementing the moves variable. And then we do some throwing, and if all okay, we create T8 exception, and as we could see here, the T8 exception just returns the number of symbols of our checked string. So then we go to the next iteration. I dumped the map string from the binary, write this simple Python script, and if I run it, we could see the actual map. So our answer is actually should be something like CyBRICS and data, then ddd r see some data r, then again, and so on. So then when we make this pass, and after we successfully make this check, we just should press enter F symbol, and a string will be printed that well done. Something like that. I guess that's all.
All right. This was a reverse medium walker. I remind you that if you have any questions, please feel free to ask them in the YouTube chat. And the next challenge that we'll cover today is going to be my challenge. It's going to be network hard, localhost. Let's take a look. So we're given an SSH access. Let's just log in. Team token. All right, setting up the environment, and we're in. Okay, so what do we have here? According to the task description, we have a box in some network, and nearby there is some peculiarly configured server. So first step is to find that server. Let's check it out. Our IP address is 10.192.1.7. Our local network is 10.192.1. Everything else. So let's, for example, scan the local network. First, let's maybe determine which hosts are up. Okay. Sorry. Okay. So we have found apparently one host, which is 180. 7 is ourselves, and 1 is the gateway. So the host of interest is 180. Let's determine what ports does it have open. Okay, we found an open HTTP port 80, and let's see what does it return on that port. All right, storage node status page, records 1, flag containing records 1, Redis configuration, a file is linked, default, system configuration, CCTL is linked, security perfect. Okay, let's check out the Redis configuration first. Okay, we downloaded it. Many lines. Let's copy. Let's copy into a text editor. And let's remove the lines starting with a hash sign. Okay. Now let's remove double line feeds again. And all right, here we have our Redis configuration. So we see that it's listening on the localhost port, default port for Redis, and pretty much it's the default Redis configuration from Debian OSs. So yeah, they didn't lie to us when they said it's the default configuration. Now let's check out the CCTL. CCTL, let's again copy it, remove the lines with a hash sign, and the only directive that it has effective is turning on a root local net. All right, that's the strange configuration the challenge was talking about. So how can we leverage that? Normally, let me open up some paint. Normally, when you get a Linux box, for example, here there are network packets incoming, and here are network packets outgoing. It's often the case that you got TCP or maybe IPv4 forwarding enabled on the box. What it means is if the incoming packets are going to the MAC address of the Linux box, but the IP address, which is not of the Linux box, the box forwards them out with the MAC address of its gateway and the same IP address. This works for any destinations except for localhost. Localhost is treated specially. So if we send a network packet with IP equal to 127.0.0.1, the box just ignores it. But if we turn on root local net, then root local net turned on, then any incoming packet that has a destination, IP of localhost, actually gets processed by the box and forwarded to the local interface where Redis is listening. So it looks like the common security measure that you just bind the port on localhost can be bypassed in this situation. For this, we need to send this box the packets with IP address, destination IP address of localhost. Unfortunately, we can't do that because, well, we can't we can't do that easily because here is our box, which is evil, which you have control of. If we, well, Linux treats 127 specially. So if we add a root on that box to 127 with the gateway of this box, well, let me just show you. So currently, I have no roots through this box. Let me add a root, for example, to, I don't know, 8s through this box, and let me listen to the traffic. Well, actually, at 0, let me ping the 8s. So now we see that we have sent a packet with the destination of 180 and destination IP address of 8s. But if we do the same thing with localhost IP, even though the destination appears in the routing table, it doesn't work like that. So if we ping 127, it just sends no packets, and it replies from our local host. So, alas, we can't use the normal Linux network stack to do that. Well, actually, during the game, some of the players told me that if we enable the same root local net on our box, then it will work. So root local net also, root local net disables special treatment of localhost. So we can't. Oh yeah, but actually the CCTL doesn't work here because we are in an unprivileged container. So we can't do just that. It doesn't work. So our option is to craft the packets manually. For example, using scopy. Let's try it. Well, let's try it. Let me just craft real quick a packet with Ethernet source MAC address, which is our MAC address. Here it is. Destination MAC address is the MAC address of 180. Here it is. Next, it will have an IP header with source address of our box, destination IP address of localhost 127.0.0.1, and for example, it will try to connect to TCP, DST or DST port, or D port, D port, D port, for example, the one from Redis. What is its port? 6379, and flags SYN. Well, yeah, actually, I want to also listen to the traffic to make sure it actually worked. So now we're going to send that crafted packet. Send P, I guess, because we have Ethernet headers. Alrighty. So we sent a packet to 127.0.0.1 localhost to the Redis port, and we actually got a reply from 180 saying CNAG. So that's looks like a win. We got a reply from the Redis service. It wants to accept our connection. By the way, let's quickly check that some other port would not accept the connection. Oh. 7.8. Answer B. Here we get reset. So the Redis actually does want to accept our connection. And then I just used a mock-up TCP client in Scapy. I Googled something like this, and I think I ended up basing off this script, I guess. Yeah, it seems pretty similar, yeah. And modifying it a bit so that it hard codes the destination of 127, and it uses MAC addresses instead of resolving the MAC addresses by IP addresses. But yeah, actually, it just emulates the normal TCP packet flow. So let's upload it and let's run it. All right, connected. So apparently we have connected to the Redis server. Let's, Redis actually understands the plain text commands, so we can just list the keys. The server responded that there is one key, and let's get it. Alrighty, got the flag. And yeah, of course, you could delete everything from your Redis state. It will not affect other teams, and it will not affect you if you repredict. So that's all for network hard crafting raw packets using Scapy. And the next one is reverse hard by Егor paired. Егor has not made the time to come here in Zoom still. Maybe he will, so I'm going to roll a record. Oh, wait. Can you move your pick on the right top? No, it will look janky. Let me show you. Like this. It's strange. Reverse hard paired.
This is right up for paired task. We were given the following zip file with 4 files inside: up1.exe, up2.exe, logic.dll, and start.db. So let's try to analyze what is up1.exe doing. Here we open start.db for reading, get file size, read file, and then we call logic your storage function from logic.dll. I will not show how to reverse this library, to fully reverse these libraries. Only briefly we'll talk about case steps. Case steps here that we have some 32 bytes key, and this DLL is used for store chunks of data up to 128 bytes. So the any process which uses this DLL can save some data, which will be stored XORed with random generated key. And also this DLL allows us to load state from some file. Here we register window class, create window, and then start translate dispatch cycle loop. This is the vendor ports which handle messages passed to this window in the command, create command to create two windows edit at the bottom. I guess we tried could try to run this application and see how it looks like. Then when we press the button, we actually will go to this code, which takes some data from the storage. We'll take the window text and then compare these two array of bytes, and if all okay, window text will be set as stage 2, and also we'll place some flag. How we could quickly find out the needed string. Let's go here, then I guess here, then we should go to the Windows mess and I guess it will be 60. So get data from storage, message box, stage 3, edit, and I guess we go here. Let's write something. So the breakpoint was taken. Now we could look which register actually contains data, and it's RTX. So that's here, and we see that actually we are waiting to dummy string here. So let's try to enter dummy string here. And now we could see that stage 2 appear in title. Now when stage 2 is set up, we could go, for example, here and try to find where this flag will be checked. And this flag is checking here actually. So actually this is I guess it's one key down. Okay, let's try to find out. I guess I could try also open it in freeway IDA, and it should know. Okay, parts. We'll create, we'll destroy. Okay, maybe this is a bit more cool way to. So let's find out where is stage 2. So stage 2. Then when we key down, this value is should be stage 3. Stage 3 is equal to 0 now. Then we goes here and we see that we should just enter string enable in the window, and now stage 3 is happening. What happens next here? If we press F button, a binary will start to send VM user message to itself with incrementing a variable, and VM user handler is what VM user is doing. First of all, it takes text from edit window and save it to storage, and then it starts to taking blobs from storage, virtual project. One moment. Actually, this virtual allow will create a rebyC mapping, so this data we read from storage 128 bytes of code and start to execute it. And this is some variable, and if sum will equal to 32, the message box will be appeared. Let's try to open, actually store.tp will be encrypted, so we could just make a break here. Here. And now I press F button, and we will see that there's some simple check. Yeah, and all 32 checks in this file, and because this function loaded from store.tp file will be checked one by one. But unfortunately, this flag is not. This is not a flag at all. This is a random string or something like that, because we did not look at up.to at all at the moment. So let's try to fix it. So we start look step. Is believe this is surround, and this is possibly time. What happened here? We add some deadbeef to the storage, and here we try to get data from storage. And I guess I missed that. Also, when we enter to stage 3, here we call add storage with K1, and we save a window handler. But why we are, and this application, despite of it saves deadbeef constant to the storage here it will load actually window handler. But why? Because of this, let's try to, maybe Ida will show it for us. This is actually the main trick of this challenge here, because let's look again at this moment. We write deadbeef here to storage, and here we extract a window handle. No, it doesn't show it for us either. Actually, this section not only read write, it also have shared flag set up, so all application which load this DLL will have the same data in this section. So if application 1 will write something to the variables located in this shared section, all other applications will see this modification. So if we go to get data from storage and analyze it, we will be known that actually we just goes through the first to last via array of saved data, and when we meet the first entry with the needed key, we will return it to us. So the application 1 saved window to storage here, then we run application 2, it will save deadbeef to the storage again with k1, but this entry will be located after the entry which is written by application 1, and they are located in the same memory. So this application 2 will have access to the storage of application 1. Then there's begin some routine. So actually all what application 2 is doing is actually creating small cell codes, then write it to the storage to index 64, and then sending a post message to the application 1, which will be load this load and execute this shell code in the context of application 1. I guess most simple way to let's try to disable this breakpoint for now. Most simple way to examine what is application 2 is sending to application 1 is just run it and look into debugger. So here we will save to the storage to index 3 the base of the binary. Then application 2 will load the will read and save to the storage a handle of vendor edit. Then it will save to the storage. Then it will be shuffle the saved string and XOR it with a bunch of 81, I guess. Then we will try to read XOR k from edit window until it will be equal to rebyC, and then we start to execute a simple virtual machine, which is also, I guess, rather trivial and could be examined by yourself. All you need is just to carefully understand what each handle is doing, and then write a small disassembler. And actually there are a lot of trash instructions in this VM, but they are generated with really dummy script, so you will notice a pattern. And this is how it should be solved. This is how the process of the solution looks like. Let's kill this application. So I copy the flag. Here I enter dummy string. Here I enter enable. Now I copy paste a flag here. Now I run application 2. Now I enter rebyC here, and so the message box well done is appear. I guess that's all.
Okay, that was reverse hard paired. Let's check whether we have some comments on the YouTube chat. Nah. Well, it's not in Russian, right? So, let's proceed with the next challenge. The next challenge will be forensic hard smashed container. It's again my task. So, here we have a video and a file system image. First, let's check out the video to see what's happening. And the video tells how we got the file system image. I'm going to mute. Actually, I feel like this to be able to enable the most pleasant quality. So, what we have here? We have some folder with flag.bmp and readme.txt. We see flag.bmp of 600 kilobytes. We change the folder. We see container.dat. Notice that the container.dat has size of 450 megabytes, but size on disk of 2.6 megabytes. Size on disk is less than the parent size of the file. This will be important later, and that means the container is a sparse file. Okay, here we see a VeroCrypt, which has the container mounted as a TrueCrypt container using AES encryption. It's being dismounted. Okay, then a console is popped up, and the container is being rewritten. And that's all. So, all right. We apparently have a situation where a TrueCrypt container has been rewritten on the disk. Let's try to mount the file system and look inside. Well, let's check out what do we have here. All right, looks like we have... okay, the file actually does not... Or maybe it does, yeah. I think it does tell us that we have an NTFS file system. Let's mount it. Over to opt. Aha, okay. Here we have some pictures and container.dat, which contains just lol. Lol with /r/n. Okay, let's look what we have in the hex. NTFS headers. Here is some trash from the container, so the container data is still there. Lots of zeros, some bitmap. All right, where is the lol? Here is the lol, and it's followed by the encrypted trash. So it seems like the first 4K the first 4K of the container were destroyed by writing over it. All right. So we somehow need to process that encrypted data from the container. Like we have to carve the container from the raw image file because there are no links to the container sectors. First thing I propose to do is to distill the image to just leave ourselves with the container data, because there are some pictures on the container, and their compressed data is also does also look trashy. So it will help us if we can just throw away the image data and just leave ourselves with the container data. For that, I wrote a script that just takes the pictures that I have copied from the container, from the image file, splits them into chunks of 64K, and replaces them with zeros. So distill.bin is the result of this script. And if we compare what we have after distillation, is this. So previously we had some JPEGs there, now we have zeros. Previously we had PNGs, now we have zeros. So now distill.bin should contain only the container's trashy parts, which are encrypted. But the next step I wanted to take, just for the convenience, right, again, is throw away all the large chunks of zeros. So I just replaced the strides of 32K of zeros with 4K of zeros, while I could do that. And I wrote that to shrunk.bin. Let's check out shrunk.bin. You see that we had 512 megabytes, and now we have like 6 or 7 megabytes. Shrunk.bin is like this. We only have small strides of zeros. Here is some NTFS bitmaps, NTFS structures. Here is some non-encrypted data also. And here is the encrypted data of the container, which starts with LOL. All right. Here is some probably bitmaps too. And that's all. Okay. Now, the next step I took was to identify the parts of the container exactly. So for that, I used Ginwale's tool called End. I just mapped the entropy of the shrunk.bin. So the tool scans the file and draws its entropy. It looks like this. So we know we have some NTFS metadata in the beginning. The parts with a large entropy, which is just picking at red, are the parts of the crypto container. And we see actually 3 such parts over our image. The first large one, then a small gap, and the second one, larger gap, and the third one. Now we need to talk about how sparse files are stored on disk. And let me fire up Paint for that. So when you create a normal file, non-sparse, it's stored on disk. Well, let's talk not about just any files, but TrueCrypt containers. If you create a normal container, non-sparse, TrueCrypt just allocates like 512 megabytes on the disk. And if your disk is relatively empty, the whole data of the container just gets landed as a 512 megabytes block on the disk. And the entire data of the entire space of the container is being filled with random trash. This is how a normal container behaves. If we create a sparse container, or dynamic, as it's called in TrueCrypt and VeroCrypt, then something else happens. A sparse file gets allocated. I'm drawing in dashes because it's not actually a block on disk. So the sparse file is allocated. It's been assigned a size, for example, 512 megabytes, but actually no data is being written on the disk. It's just pretended to be 512 megabytes filled with zeros. And we know that if we have not written some block, it's just zeros. Then TrueCrypt proceeds to format the file system on that container, and the formatting fills some block in this file. Fills some block, for example, it could be maybe 2 megabytes or something. This block is being written on disk. Then, for example, we later in time, like a week after, we throw some files onto that container. Inside the container, the files get landed just right after the file system metadata, right? But because the file is sparse, it doesn't have a pre-allocated block of data on our physical disk. It can happen that, for example, those 2 megabytes are here on the physical disk, and this 1 megabyte is, for example, here. So the blocks of the sparse file can be arbitrarily scattered across the disk. And that's what we see here, actually. Where is my cursor? We see actually 3 parts, and those are exactly 3 parts of the sparse file. So we now have this situation. 1, 2, and the third part, maybe again 2 megabytes or something, which is like this on the disk. We do not see this because the file system metadata for the container has been overwritten. We only see this part. We know that there are 3 parts, but we do not know where exactly to put them in the container, because, for example, if the allocation inside the container happens not like this, in which case we could just concatenate those 3 chunks, but it happened like, for example, what am I doing? If it happens, for example, like this, some part gets located in the middle of the container, and this got mapped here, this got mapped here. Then later in time, some part near the beginning is getting mapped, and this lands here on the disk. So the order that we see on the disk is not necessarily the same order as in the container. And additionally, we do not know the exact positions of the blocks inside the container. So it's not even enough to brute force the order of the chunks, because we don't know that spacing. So what can we do to try and analyze that? By the way, actually, it's interesting that this challenge is based on a real-life scenario. In 2018, I somehow lost my crypto container for my daily job because of running check disk, which just overwritten over the NTFS file structures, and my crypto container just all of a sudden became zero-sized. So that was that challenge. Was what I was solving in 2018 to rescue my data. I went about this like that. Let's first identify each chunk, and it can be done just like eyeballing the trunk.bin. Let's navigate with the entropy map. So we have some gap, and then the first block. Let's see. Okay, first block. Let's check where it starts. Well, it starts with lol. Okay. Here is the first chunk of the crypt container. The second chunk is before the large gap. Let's find the large gap. Oh, well, actually, let's first crop this part. Let's chop off the non-crypto container ending. Okay, that is going to trash. So now we are looking at starting from this, ending with this, and let's locate the large gap. Here it is, right? Yes, here it is. So everything after the large gap is third part. This is the third part. Let's delete the large gap. Done. Now let's locate the small gap right here. Let's carefully scroll through the... Oh, yeah, I saw it. So this one is the second part. And when we delete the gap, this one is the first part. So I have split the data we have into three parts, which I identified as the crypto container chunks. Here they are, part 1, part 2, and part 3. Now, let's analyze the format of a TrueCrypt script container. For that, I used a Python tool to parse the TrueCrypt, and it helpfully also has some specifications of the TrueCrypt header format in its README. So here is the diagram of just what's inside the container as a whole. One sector equals to 512 bytes. So inside the container, we have first sector, first 512 bytes is header, then just some random trash, then hidden header for hidden volume if you have it, random trash, volume data, which is just like user data, which we write encrypted. This is the beginning of the container, and actually we have this lost. We have lost it because we have overwritten the first part with lol, the first 4K. So we've lost the header. But fortunately, we have a backup header in the end of the container. So the same structure, like 512 bytes of backup header, and then some trash. Let's try to decrypt the backup header and see if we can identify that it indeed can be decrypted normally. So let's let's first calculate where the backup header should be located. So 128 plus 128, 256 sectors from the end of the container, which is multiplied by sector size, 128k. So the backup header should be situated 128k bytes before the end of the container. Let's well, I tried to take 128k bytes from the ending of each part, because the end of the container, which is actually like here, could be mapped either to this part, either to this part, or this part. We do not know which one. And actually the second part worked. When I took part to end, you can see that it's 128k. And tried to use PyTrueCrypt example script called dump to try and dump the decrypted decrypted header. Let me show you. Dump. Oh fuck. Import. Oh no, sorry. Python. Let's dump part 2 end, right? And we know the password. We are given the password in the task. Alrighty. Here is the raw header we have decrypted with that password. The magic value true means we have successfully decrypted it. And the PyTrueCrypt library dumps the decrypted header data just on the console. Now, let's check out what we have in the header. So we have file signature, which is true, which means we have successfully decrypted it. We have some sizes, some CRCs, but the most important for us is the keys value. That is the session, well, not session key, but like file encryption key used in the encryption of the data itself. So we need to note that. We need to save the key. Now, how does the encryption of the data work? Can't we just decrypt the data using AES and this key? Well, no, because TrueCrypt for the containers uses the encryption mode called AES XTS. What that means is it behaves like a normal AES, but you can see that the key is kind of long, right? It's 128 hexes wide, so 64 bytes. And normally AES keys are like 16 to 32 bytes, right? That's because there are two keys, actually. One key and second key. That's because of the AES XTS encryption scheme. How does it work? In addition to just encrypting the data as normal, it features a key to generate the initialization vector for a specific sector. So, if we have a crypt container, for example, this sector, and the sector is 512 bytes, AES XTS generates a separate IV for sector number 0, for sector number 1, for sector number 2, and so on. So the actual encryption fully depends on the sector number. So if we mismatch the sector number, for example, we take the data from sector 0 and try to decrypt it as sector 2, we get random trash. We get mismatching IV, and we cannot decrypt anything. So, in our case, we do not know what where the parts that we have gotten are actually situated in the crypto container file. So we do not know the numbers of sectors. So we need to brute force it. Fortunately, it's a pretty quick process, and it doesn't take too long for our just 7 megabytes of data. For that, I have written a script called decrypt sectors, which uses the PyTrueCrypt library to actually implement the decryption with AES XTS. So let's find out how the script works. The logic is like that. We give it some part of the file with random encrypted sectors. The key, I just copied it from the decrypted header. The key is hard-coded. We know that we use only AES encryption, so it's just the AES key. Now, first thing the script does is call brute force sector. Brute force sector takes one physical sector from the file and tries, from starting number to the ending number, starts to try decrypting the ciphertext of this one sector using the guessed sector position. And if it succeeds, it finishes. Try sector tries to decrypt the physical sector data that we have read with the sector number. Then it calculates the entropy. I just googled some entropy script in Python and copied it from Stack Overflow. And if the entropy is low enough, so if we did not get random trash, but we got some structured data, then it remembers the mapping from physical sector number to the encrypted sector number inside the crypto container. This way, we can brute force one sector and determine its actual real index inside the container. Let's try to run that. Just brute force sector for now. Run that on the first part 1.bin. Okay, we're getting brute forced, but actually it doesn't find anything because I'm brute forcing sector number 0, the ciphertext sector number 0. And first of all, let me open up the actual part 1, part 2, part 3. First of all, it got rewritten, but the actual data that we can decrypt starts at 128K, right? Remember the structure. So we need sector 128K divided by 512. We want to brute force the sector number 256, actually, which is the first sector of the user data. And yeah, great, we have decrypted the sector. And unsurprisingly, the first part of the container is just as it normally lands, and the physical sector 256 is the same number of XTS tweak. Second thing that we can do to not brute force the entire every container in the file, we can propagate what we already have about the mapping to the adjacent sectors. For example, we have decrypted 256 successfully. Let's try 255 and 257 with the same 255 and 257, right? So let's propagate. Okay. Every exclamation point means we had a success. Now, this one just prints the mapping it got, And show knowness map shows us what sectors do we know mapping for and what sectors do we not know. So we know actually every sector towards the end, starting with the sector number 256. And this portion that we do not know is actually useless for us because those are 256 sectors. And we know that it's one sector of the header and 255 of trash. So we actually know the entire crypto container sector mapping. Well, first part of the crypto container. Now let's execute dump known sectors, which will just iterate over the sectors that we know the mapping for and dump them decrypted in the dumped file. Let's do that. All right, let's take a look. Okay, that does not look like trash at all. It's actually a FAT32 file system. Great. 0, 0, zeros. Okay, lots of zeros. That's probably the chunk, the part that was written as the container was created and formatted. Now let's execute on part 2. Oh, but here we are trying again the wrong sector. Let's try sector, for example, 0, the beginning sector of part 2. Aha! We got that the sector 0 is ciphertext sector 3900. Okay, we wouldn't we wouldn't guess that. So again, we got the knowness map, and let's check out the knowness map. We get several sectors known, but several sectors unknown. But exactly like the previous time, the length on the unknown part is 256 sectors, and we remember that the part 2 ending is actually the backup header. We successfully decrypted backup header from it. So it's just backup header and 256 blocks of trash. So we do not care about that part. Let's check out what's part 2 decrypted. All right, there is some text. Remember, on the container there was some text. And actually, it also has a beginning of a picture, a beginning of the bitmap file. Let's finally run it on part 3. Aha. Again, 3900 and something. We have the entire block successfully decrypted. And here it is. All right, it looks like BMP data. Let's quickly concatenate the beginning of the BMP with the part 3. And hopefully for 300.bmp. And fortunately, hopefully, yeah, great. It opens up right. Okay, so that was Forensics 300's smashed container, which involved carving raw sectors from the TrueCrypt container file. Do we have any questions? Nope, we don't have any questions on YouTube. Now, let me check if we have Егор here. Real quick. Or is he still busy and I need to roll another recording? I would prefer Егor to show up here in person, but if he still haven't freed up himself from the work, well, he's offline, so I guess we need to look for another recording. Or, looks like Егор is here.
Меня уже
Hello.
слышно? Hi.
Yes, you're live.
Okay, so I can start,
great.
right?
Yeah. I have made your video full screen.
Moment. Okay, firstly, I will talk about the two gross challenges. Unfortunately, I made a couple of mistakes while implementing this challenge, so it can be solved. You can solve just second part and take the flag from the first part, but here I will talk and show you the solutions which was intended by me. At the beginning, we were given the zip file with file main and folder programs with 4 some binary files. We could see that file shows that it's just data. So I guess we could try to run main. If we run, we will see that we have some process with speed 0, and we could enter something here, but there is no happened here, so we should go and start to reverse. Firstly, I guess main file. So what this file is doing? Firstly, it's called function load program shell. We could just examine this function. So check signature, always return 1. Then we open file and call function named parse and load. All this function is doing is just read the file with our program. It expects some magic at the beginning, then it reads offset of the, I will call it code section, for example, then size of code section, then again offset in the file. We can see it here because we will make seek to this offset of the data segment, size of data segment, and then we will read a variable named entry. This is actually file wasn't stripped, so all these variable names are given to you. Then we will map to memory regions, read some data to that memory regions, and then we will unprotected code as a read to exec and fill some structure named loaded program. Okay, then we will fill name of this loaded program structures called dump program subroutine, which actually just prints for us these 3 strings, and then we will call spawn function. Spawn function will be important for us later. For now, we could see that we create socket pairs here. Then we create and fill process entry arc structures and create new thread. And entry function of this thread will be actually entry which we are read from our program file. So entry is actually offset in the code section of the initial function of our binary. And then we call also, if we all succeed, we could call add process function, which just add our new created so-called process to the linked list of running process at the moment. Then just print. Main logic of the main binary actually lies in handle request function, which works following way. First of all, we will be going through our process list and fill the poll fd array with sockets, which is used to speak with our processes. Then we make a poll system call, and for each socket which is ready to be read, we call makesyscall function. And I guess again, as in the Walker binary, if you look the stream from the beginning, IDA by default, at least this freeware IDA, didn't able to process this switch, and freeware IDA didn't have option to specify switch idiom. Maybe it's because this version of IDA using cloud decompiler. So if I do something here, it doesn't go to the cloud. I don't know, but we always can open some another disassembler and look to this function in it. So I use binary ninja here. What's happened here? This is our FD from process. This will be a size of payload. I'm payload size. This buffer will be payload. This function just looking corresponding process by his FD socket, and then we will make this simple switch, which is actually this value is syscall number. We have, I guess, about 9 syscalls here. So syscall 0 is write, syscall 1 is read, syscall number 2 is open, syscall number 6 it just read some integer from command line. Well, I won't fix all the types here. Syscall number 8 is allocates memory. Syscall number 9 free memory. Also, we have syscall number 4, which is spawn.
We somehow have a snag. All right.
What? Oh, okay.
We have lost you like in 10 seconds.
Oh. One
and
moment.
It works now.
Okay, but at which moment?
Just 10 seconds.
One moment. I will try to reduce network usage in my home network.
Okay.
Okay. So where I will end when I lost?
I think you just can like backtrack a couple of lines.
Oh, okay. Syscall number. Well, let's say just repeat what makes syscall function is doing. First of all, we read payload size, then we read our payload, look up our process. We look up process by the syscall file.
Oh my god! When you talk about syscalls, it freezes.
Syscall which locate memory
wow.
and syscall.
It actually froze once again. Yes. When you talk about syscalls, NSA is listening.
Okay, again, this syscall is write, read, open, scan some integer, allocate memory, free memory, spawn new process, and terminate process. Right? Am I here still? Okay, and after this call is executed, some return value will be written back to the socket of our client program. So let's try to examine the shell binary at the beginning. I just load it as binary blob because of the format is pretty simple, and this function is the entry point of our shell binary. So let's try to understand what happens here. This function, okay, another important moment that when we spawn a program, we pass the process entry args here as argument for our entry point. So this arg1 is actually a process arg structure. Now we could create members at this offset. So this will be syscn, this will be, I guess, fd, and this will be padding, and this field will be, I guess, it data. Okay, so what happened here in this function? As we can see, we will call syscall function, and we could see the number 8. Again, if we return to the main binary, syscall number 8 is actually malloc. So this function will be named as malloc. This function use integer 1, so this will be I guess a read. I guess I know. This function is just strcmp, and this is actually sleep. Okay. In order to understand that this function is actually sleep, we should also examine syscall function here. So we have some syscall param structure, which is pretty simple. It have file descriptor, then it have pointer to the payload and payload size field. So if our payload pointed to 32, it's just a sleep syscall. So this is sleep function, and I guess we also should find, yeah, right, right, syscall. So how the shell binary is working? It just allocates some memory, then we read from fd file descriptor number 0 to this memory, replace end of line character, and then we would make a bunch of strcmp function calls. So let's try to, for example, this will be all strings are just stored in the stack in these binaries, and we could see that we have 3 commands: spawn, exit, and sleep. So if we are, this command is exit, this will be spawn, and this sleep. So let's try to write spawn here, and we could see that now we should enter the process name. I guess I have some echo binary here. Then shell binary reads from us again, and then echo start reading. So I write something again shell, and we could see that echo actually outputs entered string. Why this reads? Why we see these reads here? Actually, it's because our my operating system, so-called, executes syscall one by one, and each syscall is blocking. So when we run echo binary, what happened here? I entered spawn. At this moment, only shell is running. so I see the result of the write syscall of the shell binary. Then I entered binary name echo. Again, shell. At this moment, echo binary was spawned, and it calls allocate syscall. I guess I could show it. It will be a bit more. So after run, echo binary will call allocate syscall. This syscall will be executed, and then after that, this syscall read from shell binary will be executed. So we could just enter the empty string here. This will be important for us while we will try to extract first flag. So I have echo binary, which actually did nothing except read string from us and then write it back. Shell binary is actually just used for spanning new binaries. Also, we have cut binary, which is okay. Again, allocate, then read. Then this function is check that past file name didn't contain any dot, and we are supposed to read the flag.txt file in the first stage. So we are not able to do it via the cut file. So check dot. And again, this call number 2 is open. This is call is read, and this is call, I guess, will be write. Yeah. And again, this is call number 9 is free, and this is call, I guess, exit. Yeah, number 5. Also, we have storage binary, which implements the simple interface for allocating and deallocating chunks and work with them. So I could run storage, then I could run sleep function. So when I call sleep for the shell process, its thread executing this shell binary will be sleep for 5 seconds. So all prints of storage binary would happened quickly for us. Okay, single alarm happened. Let's try again. Spawn, storage, sleep. Oh, I guess there's something like erase happened here. Okay, so we have allocate, for example. Oh, okay. We should enter index 0. Happen again shell 32. Then we could, for example, print, and it's OR. So where the vulnerability exists? Here in shell binary, let me quickly to restore all function. Allocate, print menu, read, alloc. This alloc not allocate this call, but alloc function of storage binary. Free, edit, and print. Right. So the main idea is following. We could allocate some chunk in storage binary. Oh, okay, let's examine free function. Free function is actually a free chunk, but didn't clear the pointer here, so we have use of the free vulnerability. And the idea is following. We create chunk in storage binary, we freeze this chunk, then we run cut binary, and then after the cut binary, after we enter some dummy file name in the cut binary, we should rewrite this file name from the storage binary, and then cat will be opened flag.txt for us. If we look at the exploit, it's look something like that. There's only some one important thing that we should carefully order all operations because of blocking syscall nature in this so-called operating system. So I just spawn storage binary, then I send shell to sleep, then I allocate and deallocate this chunk, sleep 5 seconds, then I spawn cat binary, and after cat binary is here, receive the file name as que, I rewrite this que string to flat.txt in shell binary. So I guess we could run it. There's 5 seconds sleep here. So this is a first flag. Also, we could run it with debug parameter and see how this, which data is flying over the socket. Okay, this is how first part was supposed to be solved by me. The second part is required to get shell from us, and again, because of I forgot to forbid calling free several times on same chunk, it can be solved via some heap cache technique, but the intended solution was to, again, via use after free, just rewrite these process anti-arc structures, so we could, for example, replace this fcan field to system address and the pointer instead of fd value, we could write something like /00. So how it could be done? In second exploit, I didn't make this dirty hard coding. I write a bunch of helper functions for me. So for example, there's wait for edx function, which is just read until the main process is ready for read some data from us. Then I parse the process ID, and if this process ID is not mine, not one which I expected, I just send empty line to it. So we have make alloc function, make free function, and this function is pretty similar to this function except that it also read answer from expected process and return it to me. First of all, we should leak a libc address. This can be done via, for example, allocating some big chunk, then allocating a guard chunk, then we free big chunk, and via the use after free, we could read the address inside libc main arena. Actually, libc address wasn't given. libc was given to players, so how it's supposed to be find out exact libc version? First of all, I again extract this libc offset, and because of I know offset of my leaked pointer from main arena, I could calculate address of main hook. Oh, sorry, main hook, malloc hook. So actually, this print will be printed for me address of malloc hook in the remote libc. So let's try to run it. And this is address of malloc hook. So I could just go to the, for example, libc cat malloc hook. Am I still here? Because it looks like something lagging. Okay, so we find a bunch of possible libcs. So after I create my exploit, tested that it works locally, we could just go through some of this libc. Actually, obviously, this one is not suited for us because it's for 86. So we have 1, 2, 3, 4, 5, 6, 7 libcs to brute force. So we need just take this offset and this offset. What's happened next? We allocated 4 chunks with size of 24 because of this structure allocated also with 24. Then we freed these chunks, and then I spawn a new shell binary and read it sees process arg structure via use after freeze. So let's try to do this. This is pointers from unsorted bin chunk, and this is our process entry, process arg structure. So this is a file descriptor. This is the address of the data section of binary, and this is the address of system sysfkn function. Here, for some reason, I don't know why, I calculate binary base, and then I just forge all what I need to get shelled. So sh00, some junk 12 bytes, and then system address. So okay, I guess I forgot to save the file. And we got a shell, and we could read a second flag. Well, unfortunately, we could read a first flag also. I guess that's all for these 2 tasks.
Right. So, do you want to proceed to the next task?
Okay, if there's no question, let's.
Oh, let's check. Well, just some Russian guys complaining that we talk in English.
Okay. And I guess the last challenge which we will. Okay, the last challenge which will be right up today is one moment. I found it here. It's called.
Yeah, the unsorted tiles are really causing the pain in the butt.
Digital signature challenge. So it has some description here about the pizza lover. What's important for us that we were given some. We were given digital signature.zip file, which contains actually following files. Let I extract it in something new here. Okay, this archive contains 4 files: flag.enc, main.elf, res.png, and signature from bin.png. If we look at these files, we could see that res.png contains some, I don't know, curve maybe, and the signature from bin contains some ASCII art, which looks very similar to this one. So let's try to quickly analyze this main.elf binary to understand what it is doing. Actually, I already analyzed it. First of all, it asks for some length from us. Then it allocates in the stack a bunch of Fourier coef structure which is contained from 3 doubles. Then it calculate I don't know how it's called correctly, some Fourier series transformation, and then this function will form such a ASCII art and use it as ISK for decrypting flag. How we could find out that this is actually IS? We could use some, I don't know, maybe IDA plugins, or we could just take some constants from here, for example, something like that, and send it to Google. And box. Okay, this is look very. Oh, okay. We could see that this code is just emulate ISN construction. Maybe if I write it some other way. Oh, yeah. In GDL this box. So this is actually IS, but it didn't change anything for us. Actually, main part is happening here. This function is calculate something Fourier series transformation. So what we should do, we should enter some Fourier series coefficient, then this binary will form for us following ASCII art and use it as ASCII key. First of all, I googled some script which is for Python, which is calculate these Fourier coefficients from the points. How it works, it takes a bunch of points that these points are sorted in order to make the picture smooth, because otherwise it will be jumping between the dots in the random order. No, well, not random, but in order which is it will be added to points list. So this function is third point, and it's actually pretty slow works, because for each point we are finding out the closest one in a list of remaining not taken points. Then I googled some, I guess here, JavaScript code to transform complex coefficients to frequency, amplitude, and phase. And then I just pass this coefficient to the main ELF binary. I guess I could try to do it. This almost work because of, let's try to, I run it with res.png. Now we should wait for some time. A small spoiler, this didn't work fully for us because we get some ASCII art, looks like this, but it won't be same as one from the given picture. But this step was crucial for me because I was too lazy to OKR or maybe rewrite this ASCII art from this picture to the text form. So when I have some very similar ASCII data, I just fixed it. So I saved it in file eta.txt, and then I try to do following. I try to upscale this ASCII arc because of res.png has a resolution, I guess, 290 to 1270. So I create following picture with dots named A. So basically I just multiply each coordinate to 10, I guess. Then I form a new picture named lined here. Maybe script. Okay, it will be end soon. So this picture looks very similar to wanted one, but not the same. Actually, this picture didn't look as exact wanted pictures either, but when I have such pictures, I just run paint and start to using my paint skills to fix some places where the downscaled picture was wrong. So there is here some bunch of pixels. Also here's my changes here, and so on. It takes me about 40 minutes, I guess, and mostly just because of this process is not very fast. But I guess maybe the more right way to do this was not creating these pictures, but using some line equation and calculate these points, these sorted actually points in the script. But anyway, I guess I spoil enc.txt file. So I enc here. So if I run it.png, it will be correctly decrypt flag. I guess that's all. So let's wait for successful decryption. And if you have any question at this moment, I guess I can try to answer them. By the way, I didn't understand. Is this some word or
Yeah.
I see Crusoe here.
Yes, yeah. Actually, it's like in the task description that the guy is named Mike Caruso. It's his digital signature.
Oh, sure. Well, I didn't read task description. Usually.
Interesting. Could you cache like the sorting of the points so that you are not waiting every time?
Oh, I guess, yeah, I thought about it about after half of an hour, but I guess in next 10 minutes I finished, so but again, when we have this picture, let me try to find it. Yep, we got the flag here. This picture with dots are sorting pretty fast, so I just use a line equation to make a bit more points, to add more points, and they will be sorted. So I guess I could tune the quality. by adding these points from a line from, for example, this dot and this dot.
All right. You're currently sorting the entire lines, right? Every point.
Yeah. Because my current code is just taking all pixels not equal to white, and then sorted them.
Right. So that was the flag from the flag.env that was given to the players, and
oh yeah,
similarly, you could
you
just submit
should. Right.
Just
No,
submit to the
unfortunately,
server.
my script didn't save them, but
Alrighty. So I guess that's all for today's task analysis session. Thanks so much, Егor, for joining live over Zoom. Thanks, guys, for listening to our write-ups. I remind that we still have the web hard bounty unclaimed. First 3 teams who solve the fixed check-in web hard will get a Amazon certificate. And I know at least 2 guys who are very, very close to solving it. I think one person will maybe write like these minutes will claim first blood, but there are 2 more open spots, so good luck if you're interested in web and crypto. And hope you join us for the next edition of CyBRICS next year. And that's all. Thank you so much.